Okay, so who want to start? Maybe not the first group. We can start with the group 2 and 3. And what are your thoughts? What do you propose?
Non, monsieur, on pensait une TFT.
Okay, so you want to do it in French?
Or in English.
In
English, please.
In English. Let's go. So what do you propose?
Group 2 or 3?
As you wish.
On the group 2, we propose the time-dependent density functional theory.
For what? So this is a theoretical method. And to calculate what?
The absorption spectra and homolimo.
Of what?
Of the molecule.
Okay. Do you need the TDDFT, the time-dependent density functional theory, for the homolimo?
I think no.
So, do you propose anything else also?
I don't know if it's true, but we can find the molecular terms and apply the transitional rules to see if there's permitted transitions, and then know if they're phosphorescence.
Okay. And the group 3.
We discussed and we proposed to do at first. We build a little crystal composed of small molecules, or I don't know, 2 molecules on Gaussian with the Gauss View software, and then we launched the optimization of the structure using DFT, for example, and bit-relip or in a basis set, but I don't really know which basis set. Maybe a basis set using polarization. What's the name? Polarization functions, and also on AV atoms. So 631 plus GD, for example, and to obtain the optimized structure. And then afterwards we send the TDDFT calculation to have access to the absorption spectra of the molecule, and also then to the emission spectra.
So I've launched the stream, by the way, and I tried to write what you were saying to me, and I hope I didn't miss too much information. Okay. You told me the geometry, and then what? I didn't recall if you told me of anything else. So you told me at least a dimer to reproduce a crystal packing or interactions.
Yes.
Then a method, Gaussian, compute the geometry, and
yeah, we optimized the geometry of those two molecules.
Ouais, yep.
To find the most, optimize in energy to find the most stable what's the name?
Okay.
Geometry for the both molecules.
Okay.
Using DFT, for example.
Okay.
And afterwards, when the molecules are optimized, we launch the TD-DFT calculations. On the ground state optimized geometry.
Okay, and what do you have with the TD-DFT?
It gives us the absorption spectra of the molecule of the dimer first, I guess.
Yep. Okay.
And then I'm not sure, but it must be in the inputs, but we should be able to observe the emission spectra afterwards, or we need to maybe optimize the first singlet state before, maybe to be able to observe the fluorescence of the molecule. I'm not sure about this.
Okay. Thanks. Rania, what do you have to complete, change, or add?
We discuss on a à peu près la même chose que le groupe 2. We think like the group 2, and we also think about the impact of the bromine and the aldehyde function, and we thought that we can try to modelize the molecules with and without them to understand if the luminescence is due to the interaction between them or not.
Okay.
And it's all I have to add to complete what the group 2 said.
Okay. Thank you. Well, so here maybe I would maybe propose, or maybe you should at first, and I'm not sure that you didn't do that, because in your restitution you tried directly to go to the list of the calculations. You should start with listing what are the propositions that you want to check. So in our presentation of the article, we have seen that there is a fluorescence at the liquid state. You have a vibrational relaxation between T1 and the ground state in the liquid state. But when you go in a solid state, you don't have any more vibrational relaxation. Up. Since I like your you have a phosphorescence at the solid state, so that means that the emission state is different. You have an excimer between two para-bromobenzaldehyde in the solid state, and you have no excimer between a para-bromobenzaldehyde and a para-dibromobenzene. You have an impact on the emission wavelengths of the lateral chains and of the pi core, and you have an impact of the bromine and aldehyde through the interaction between the two. Okay, so this is the kind of information that you want to discuss with theoretical calculations.
And why fluorescence at liquid state is a hypothesis?
No, okay, yeah, you're right. I'm doing the skeptical role, and maybe I don't have to overemphasize the skeptical part. Okay, so there is probably there is fluorescence. The thing is that the hypothesis is that there is emission, and they say that it's a fluorescence, but you're not sure that is really from a singlet state. There is no proof in the article that this emission in liquid state is in fluorescence. Maybe the interaction between the in the solid state change drastically the energy levels, and you change your emission spectra just by the solid state interaction. Okay, but the most reasonable approach is that it's a fluorescence. However, we could discuss on this. The same here, that's why we can put here scientific results. There is an interaction between aldehyde and bromine. We can see it by an X-ray diffraction. So it's not an hypothesis. What is the hypothesis is what is the real, or what is the result that we want to prove, disprove, or discuss is the impact of the bromine and the aldehyde. I didn't start to discuss what kind of calculations yet. I just want to list what are the information that we could discuss, or maybe we would like to discuss. And here we can discuss also the blocking points. Rania came back to me to ask me some legitimate questions. Here, the first and main blocking point is solid state property and molecular materials. Property. Okay, so we can do solid state calculations. However, when we talk about solid state computational chemistry or solid state DFT, it's for fully crystallized and fully periodical systems, more like NaCl, pure solid states. That means that you will have a repetition of the atoms in all directions, okay, and you will not use local orbitals, but you will have a periodical orbital, and it is quite different in the approach. What is really problematic is when you have a molecule, so you have a property that is a molecular property, and you have a solid state interaction, but the main property is driven by the molecule. So you need a molecular approach with Gaussian and localized orbitals to really fully understand, and it's because it's cheaper and more precise to have the properties. But when you do molecular calculations, you have functions that are not adapted to long-range distances. That means that let me write something. Solid state theoretical methods are adapted for purely or inorganic solids. Molecular properties needs Gaussian localized orbital functions. That means atomic functions, and they are more precise. You can do you can get more information. However, they are not adapted to long-range interactions. Dispersion, for example. Dispersion, van der Waals. Dipole, so on. That means if you have some hydrogen bonding, since there is an overlap of the wave functions, that means that the atomic electrons, the electronic density of surrounding the atoms see each other, they overlap, you will have this information in quantum chemistry. But if you have a long-range distance that is more in the more diffuse part, you can add diffuse function, but the space covered by the quantum chemistry is generally shorter than van der Waals interactions. So, for example, p stacking is quite difficult with molecular quantum mechanics. You can add perturbations terms. That means you can add some terms in your basis set, but your method, in essence, is not fully adapted for this kind of problematics. So here we have quite a huge blocking point. The properties that we want to understand depends on solid states and probably intermolecular interactions that are in parts weak. Officially, what is put in the article is that the bromine and aldehyde, there is an overlap and there is a strong interactions. Maybe we can try to see if we can compute this interaction. If we cannot compute this interaction, that does not mean that there is no interactions. That means that if you consider just two molecules in gas phase, there is not this interaction with quantum mechanics. Okay, so it's probably our method that is not adapted here. So here we have listed a part of what are the results and hypotheses that we want to discuss, maybe some blocking points, and now we will discuss of what kind of calculations we will use. Okay, so this is the part to the inputs. That means that the input is the file, the orders that we must give to our computational chemistry program to compute what we want. And we need a computational strategy. A strategy, it's because we need to list what kind of calculations we need. The first group that answered just before gave us the last answer. That means we compute TDDFT for absorption properties. To do that, you need steps before. Okay, so you need to propose a strategy. That means you need a coherent approach with relative steps that are well organized. Computational chemistry is based on approximations. The Schrödinger equation, the quantum mechanics, is okay, but we cannot do it for more than one electron. And chemistry is always something that depends on much more than one electron. With the benzene, you have like 30 electrons, and with here our systems, even if it is a small molecule, you have much more than one electron. So you cannot do perfect quantum mechanics. You need approximations. That is why in 2 days you will have Denise Crow class to teach you what kind of approximation you can use, and I quite enjoyed here. That means that you use adapted parameters. That means that you must choose the correct method, or a reliable method that will give you a correct answer with the correct parameters, and not approximations that are too strong. If you have a too strong approximation, it will be fast, but probably it could be wrong. So you need something that should be correct. And we know that by experience, and we know that by some mathematical proof. And that means that, yes, when we do computational chemistry, there is like some artisanal knowledge. What are the methods that usually works for this kind of problems? So you do some bibliography, or you have classes, and we will teach you here how to compute molecular properties with emission, absorption, and so on. Of course, 10 years ago, or in 10 years, the approximation and the method will be even better, because we will have more computational power. However, the approach will be the same. So we have absorption properties, we have emission properties, and we have a Jablonski diagram if we want. And yes, you are correct. So we need a coherent way. That means coherent approach usually means same approximation along the way. That means that when you choose an approximation, it's better if you use the same approximation all along. That means that for absorption properties, you need ground state plus excited state vertical energies. So if I go back, for example, or if I look at the Jablonski diagram, we always need, when you do some spectroscopy, you always need the ground state information. You need a correct, relaxed ground state. So that means, and that's what we've told me here, a theoretical method to compute the geometry of the ground state. So here you need an optimized ground state. And we need the vertical energies. That means that you compute the energies that goes to the ground state to the different singlet or triplet states. With that, you can have the absorption properties. Here, to have, and I will go back in more details right now. Don't worry. Just that I explain what is a computational strategy. To have the emission properties, your colleague quite proposed wisely that if you want the emission property, you need the excited states are their lowest energy. That means that you need to have the geometry of the singlet and triplet at their minimized energy. That means that you need to optimize the energy of the singlet and triplet to be able to understand the vertical relaxation by radiation. Okay, so you need optimized ground state always. You need excited vertical energy to be able to know which excited state you want. Plus, you need more optimized excited states. Usually, with the Kasha rule, we expect that the emission will come from S1 or T1. Okay? So, if you have now optimized, if you have an optimized ground state, you have the energy here of the S1, F2, F3, T1, T2, T3. You optimize S1, you optimize T1. Okay. If you want the full Jablonski diagram here, what do you need?
Sometimes we add absorption.
Again, so the absorption and the emission. Okay, so with what you have already calculated, we have the green arrows, red arrows, or at least the arrow here, and you have this one. What do we need to complete the diagram? Théo, Tony, Majid, Liam.
Oui.
So what do we need to complete our diagram? What
I don't know.
here in this diagram, what are the information that you don't have already?
The energy of the triplet, no?
We can calculate the energy of the triplet because in quantum chemistry you can calculate the direct absorption and excitation energy of the different triplets. You can optimize the triplet. What he will tell you is that the probability is 0 always. Okay, so you will have the arrow, but it will have a 0 probability. Okay, so this one we have it if you ask for the triplet. By the way, that means that here, if you want the excited state energy, you need to choose S, singlets, or triplets, or both, but you will not have the triplet if you don't ask them. Okay, so what else we don't have.
We probably have to optimize the S2 state.
Maybe excimer formation that was discussed in the article.
Okay, you have the excimer. Here you don't have the excimer. Okay, so I will add that. It's not the answer that I was looking for, but it's an interesting answer. Excimer. Okay. But here in the Jablonski diagram, and in relation of what we have, there is one physical phenomena that we didn't discuss and you've never heard about in calculations. The optimization of the S2 is maybe not mandatory. If you optimize S2, what do you expect? And why do you want to optimize S2?
Okay, okay, I understand. We want the non-radiative relaxation, but I don't know how we can get it with calculation.
Okay, so
and
here
I want internal conversion, but it's the same thing.
Okay, so here in the Jablonski, you put easily intersystem internal conversion, intersystem crossing, and non-radiative. But how can you be sure, and how can you do that? How does it work, non-radiative relaxation?
It came from vibration of the system.
So a non-radiative relaxation, that means that without emission of photon, you can lose energy. And usually it's a vibration of some part of your molecule. So we need to compute the frequency and normal modes of your molecule. Usually, the frequencies and normal modes are advised to complement the optimization of a ground state to check if it's really a minimum. But when you do the frequency calculation, you have the vibration of your compound. So you can picture if you have some kind of vibrational relaxation that can goes from T1 to the ground state. To be more specific, what you will see is that sometimes T1 is at a level that is here, for example, and you have vibrational energies or vibrational levels up to here. So if T1 can coincide with some vibrational levels, maybe a first harmonic or third harmonic, it's a low property, but it can happen. It can happen all the time, and it will happen. And you will lose rapidly your energy. If your first singlet has a low energy, once it is relaxed, your bar here is here, and you will have easily a pass to a vibrational energy. So we don't have the full calculation of the overlap between the vibrational modes, but just looking at the energies okay, and with the frequencies that you can calculate here, you can have this kind of information. You can picture and propose a way of non-radiative relaxation. If the two systems here, for example S1 and T1, are really apart in energy, the inter-system crossing will not be favored. So it will be too complex to go from 1 to 1. It's an energy up, and it's much better if you have some kind of vibrational crossing, and you can do it with the vibrationals of your systems. Okay, so that means that to have fully this part, for example the inter-system crossing, you need the frequency of the optimized excited states, and this is super costly. To do an excimer calculation, that means that here, the excimer, you need to compute the dimer, the solid state, okay, dimer interaction in quantum chemistry. So, to have the absorption property, emissions property, and Jablonski diagram of a molecule, it will be okay, and we will have reliable answers. To do excimer, we will try to do the dimer interaction. We'll see if in the ground state it works, and if it works, maybe we can check for excited states of this dimer. The computational strategy approach is what I want you to understand in this class. That means that this is not a practical work where you need to learn today and this week how to configure an input, how to launch a calculations, how to extract data. In 2 or 3 months, it's all forgotten. What I want is that you are a scientist and you are making, you're working on molecular materials, and you do some experimental work, you have some hypothesis or you have some results, and you know that probably you can compute, modelize some of this data, some of this information. Maybe you can play with the computational approach to really check the relevance of your aldehyde function, your bromine, or can do the linker is important, what kind of linker we should use, or maybe you have you have a result that is quite satisfactory, but you will like to do some calculations and try to optimize your results before going to hard and costly experimental work. So in your Moodle, you will see that you have a document that is a doc of this class, where you have a table of content. You will see the bibliography again. You will see the calendar that you already know, and you will have the previous examens of this class. Okay, so I will try to take some time to discuss about maybe try to do some corrections, okay, but it's up to you. You will see that Denis Jacquemin it's pure learning questions. That means that you follow the class and it asks you some questions concerning the class. Whereas in my part, you have a part of an article, and I ask you to comment on the computational strategy, to say, oh, how can we compute, for example, this property. Here you have, for example, a photochromic approach, and you have here, for example, using a quantum mechanics approach, propose a series of calculations to study the hypothesis and results of the scheme 1. That means that I want you to understand what is the ground state, how can you calculate a ground state, how can you characterize a ground state, how can you characterize the going to an excited state, an absorption, an emission, okay? And it's part of what I expect you to know. And I say again, my objective is not to form theoreticians, but to form scientists that knows what can be done with computational calculations to help them, or to break some blocking points, for example, or to optimize the results. And probably you will not be the one that conducts the calculations. However, there is a Julie that is now a PhD in ERDIS, in electrochemistry, and she came to me. She was quite proud. She came to me with a scientific problem, and she already thought of what kind of calculations could be done and so on, and she told me if I had time to do it. And I told her that the best is that she do it and I help her, and she has done her own calculations for the PhD, but at least she came to me with an already discussed computational strategy, or thought computational strategy, and that means that if I was the one to do the results, the computational strategy, the calculations, she would have understood the results much better, because calculations, it's not magic and it's not perfect. And it's too easy to say that calculations is approximation, so if there is something wrong, it comes from the approximation, because experimental work is also deemed with approximations, or at least you have facts that are sometimes too complex or too indirect, and you take some, in your discussion, you use hypotheses that are sometimes hidden. So the interesting part is that you're young, you're finishing your master, you are in a polydisciplinary approach, and you can be aware of all the limits in all the domains. Okay? Let's take a final break. Okay? 10 minutes, and we'll finish.